So on that note, I'd like to introduce Margaret. It's a very great pleasure to have her over from the UK. She's a distinguished engineer, starting out in Torness Power Station in the 80s, and then moved to Culham in 1988, I believe, and has been there ever since. She's currently the group leader for the ion cyclotron heating? Resonant heater, that's it, yeah, which is part of the jet fusion project in Oxfordshire. But also she's a very illustrious member of the IET. She's a fellow of the IET and is involved in accreditation and all of that sort of work, and is on several committees within the IET, so she's come over on two counts, I suppose, for tonight's talk. So on that note, I'd like to welcome Margaret to the podium to deliver tonight's presentation.
Good evening, ladies and gentlemen, and thank you very much for a very warm welcome. It's lovely to see so many people here tonight. So when I was asked to do this, I thought, okay, well, I'm going to Dublin, and what am I going to do? So I thought, yes, I don't know what people know about fusion, but I have a great love for it, and I hope in my lifetime that I actually will get to see it happen. So I'm going to give you where we are at the moment, a breakdown of how things work. So some of the basics of the plasma, the fusion physics. Those who don't know it, I think I've got some great colleagues here who know a lot more. An introduction to jet, obviously that's the main machine I work on, and so I'm going to go, a lot of the explanations will be based on that. I'm going to explain some of the terminology and technology, and then I'm going to explain some of the challenges that we have and the progress we're making, some of the future, where we're going to go, and what happens. But first, and as sort of an introduction, I'd just like to say, why do we need to do this? So we've got a map of the globe. This is just based on what our current energy needs are. This is tons of coal equivalent. This is at the moment. This is based on what we use currently in the world today. Now, if we wanted China and India had the same access to the energy that we would want, then pretty much what would happen is, depends on who you listen to and what calculations you have, but there's sort of three variants. Some people say it will double, some people say it will triple, and some people say it will quadruple the amount of energy that we would need as of today, even if we don't take the population. So even taking that, and you take the world population, we're continually growing, and our demands are much, much more all the time. And if you extrapolate this up to 2100, you can see that we're going to have a huge or massive energy demands in the future. Now, obviously, the way we do it at the moment is with fossil fuels, oil and coal. So what we need to do, if you then take over the past time, you can see the fossil fuels of all the world, conventional oil production will peak in about 5 to 15 years. If you then put the additional demand that will be on there, especially as you know that China, India and the other countries are coming up, then that is going to get much, much more. You can see here from this graph, and I don't knock any energy source. I mean, research, I've actually embraced all research, and including the things that fail, because a lot of things that actually come out of that are from failures, and that's in all things. But you can see here in 2008, so we go 2008 here, you can see actually where the price went up, and you can see that dip in production, things like that. So you can see if we start running out of things, that's going to have a huge impact on the energy that we're going to have in the future. And of course, one of the big things that we hear about all the time at the moment is global warming. And there's not anybody here, I don't know, I live in Oxfordshire, and the one thing I've had to go through all this winter is over or around very, very big floods. So it's had a very big impact on what we've been talking on the press. So therefore, what we have to do, we've got these renewables, we've got all the other things, but we need a base system that we can use in the future that's going to have or cope with these huge energy demands that we're going to have. And I've put together the things that I would expect that you could have. You could have the fossil fuels, we could still use it, but we'd have to have carbon capture, and that's another lecture in itself. We could have fission, we could do more work into fission, get better plants, I'm sure that could work, and we could actually go down that route with all the pluses and minuses that go with that. We can have fusion, the people who know it have magnetic, that's the magnetic I work with, or the laser, in fact that's some articles are coming out at the moment about laser. or a technology yet to be found. As I say, I don't dismiss anything, so I don't know what's out there, and somebody could have a very bright idea. We're all engineers, so that's something we would hope that could happen. So my question tonight, and my lecture to you tonight, is could fusion be the solution? Could we use fusion? So what is fusion? Now I love this bit because it's one of the things, I like sci-fi programs, that's what they do. Men, you love to have your shaves and you like to use fusion power. It's not quite what we're looking for. Back to the Future, that car, you just dump in the rubbish and off you go and you've got fusion power. I'd love to do an analogy to see whether this could ever have any things on there. But my favourite, Iron Man, his heart plug in and we've got fusion. I should have put Spider-Man up there as well, because of course you know in Spider-Man he also had a fusion system in there. Of course I'm not talking about this sort of fusion, it's all futuristic, we all know, and we could all say that science fiction does come true in some cases, that's very, very true. So what is fusion? Fusion is a power source, we all know the sun. It's very, very good, and what it does, it combines light nuclear, puts into heavier, so you get hydrogen into helium. Very good process, we use it, in fact some of our solar power energy comes exactly from this process that we use. But if you take that and you want to put the sun here on Earth, it's nicely in a vacuum space and it's very large. That's how it can fuse as the way it does. And I've got transited Venus here, which is 86% of the diameter of Earth, so it's very close to what the Earth is. And as you can see, now we're trying to fit the sun on Earth. It's going to be very, very difficult. So how are we going to do this? What do you do? And this is what the research that we're working into. So, to do fusion on Earth, what we can do is we can take the isotopes from hydrogen, that's deuterium and tritium, and we can put those together and get them to react. And what you get is you get helium and neutron, and you also get energy. And then you can use that energy, this is what it is, to then power your future power plants. But we've got to work on this. How's that going to happen? Well, what happens is by the Lawson's criterion, apparently, if we get the plasma density high enough, the temperature high enough, and the confinement time is sufficient to do that, we can get fusion here on Earth. So typically, as you can say, we need to get. So we haven't got the vacuum of outer space, so we can just try and get density in a vacuum, and that has to be 1,000,000 times less than atmosphere, so we have to have a good vacuum. We have to get temperatures up to beyond that of the sun. If you think about the sun, it's in the centre, it's 15 million degrees centigrade. You need to get it 10 times hotter than that, plus, and then you need to have a confinement time of 5 to 10 seconds minimum. And this is just to have your Lawson's criteria to get the same amount of power out that you're putting in. Now, I've put on the right-hand side of gas to plasma. If you take a gas and you heat it up, I think it's about above 6,000 degrees, then you can get a plasma. It's where the electrons come away from the ions and you get a soup of electrons on there. So using this is what we use. So around the world, we've all gone into this and they've sort of thought, right, let's use this. Let's take this plasma, see if we can do the sun here on Earth. And throughout the world, they're working on these at the moment. And there's lots of different tokamaks and vessels, stellarators, and different vessels to try and look into this to see how it can be done. There's the USA, Canada, Asia and Europe all working on this. But now I'm just going to concentrate on the aspects of the Culham side and what the systems that are there. So this is Culham. This is where I work. And what we're very lucky to have is the JET, or the Joint European Torus. This is the biggest, it's the only tokamak in the world at the moment that can handle tritium. And we also have a spherical tokamak, it's called the Mega spherical tokamak, or MAST for short. And that's just a British research programme, and it's independent of the JET programme, and it works on one side on the same side. So we've got the plasma, it's going all over the place. If we just put it in and try to bottle it, you then have all these, because it's hot, it's going to hit the sides of the walls, it's going to deteriorate, cause problems. So what you can do is you can apply a magnetic field. And what will happen is that with that magnetic field, the particles, the electrons and the ions will rotate around the field lines, as you can see there. As you can see, they all go in opposite directions because of the fact of the movement through a magnetic field. One of them charges is positive, one's negative, so the right-hand board you can get, they're on the opposite sides. So with a magnetic field, you can apply that, but if you had it in this bottle shape there, it would just escape out the outside. So what you can do is put it in a tokamak or a magnetic bottle, close the ends, and you can confine it with a magnetic field. Now, the way JET works is you can see the inner poloidal, the coil through the middle there, and what you can do is you can drive a current through that centre coil and just quickly reverse it, and that induces a secondary current, or like a transformer, into the plasma itself. And by doing that, what you do is you drive current through the plasma, and therefore you can see you get this helical field lines around the outside, which confines your plasma because, of course, it's charged. And so therefore, with that, as long as you're driving current, you can have this plasma. The fact is, because you've got a current flowing through there, then what happens is you'll get a heating effect in there, just naturally by the current flowing through there, called the bootstrap current. And that's about 50 million degrees centigrade. Without doing any additional heating or anything else, just with inducing that current, you can get quite some heating in itself. And you can see here some of the coils. We've got the poloidal magnetic field, which goes on the outside there, and the toroidal magnetic field, and then the resultant helical field around the outside of the plasma. And then we've got some shaping magnets there also, so we can actually change the shape of the plasma, so we can have it flat, or we can have it triangular, or we can have it even smaller, and we can actually play with those limits to whatever physics they require. So here's JET. This is, if I just do a brief explanation on here, so we've got here, these are the radio frequency, 23 to 57 megahertz system that works in there. We've had in this about 16 megawatts of power into plasma. We have here a diverter, or a pump diverter. That's the exhaust of the system, and that is currently, what you have is you have the field lines going round here, and that means when you've got your heated plasma particles, they come out, they hit the FIET field lines, they then come down to the bottom here, and this is actually cooled with cryogens. So what happens then is you get that cooling effect, and you can get these waste particles there, and it's to the exhaust. It then sticks to them, and later on you'll heat that up and then release those particles and then cool it down again. That's something that has to be thought about for future devices. So what we've got in JET is we've got the fields. We have up to 4 Tesla in there. We've got plasma currents, and I think we routinely operate about 2 to 3 megaamps. We've got major radius about 3 meters, with a plasma volume about 80 meters cubed. And I've just explained we use the diverter, and that's just an exhaust mechanism, and that will have to be worked on, and I'll come to that a bit later on. One of the things we did in the 97 experiments when we put tritium into the machine is we discovered we used to have graphite carbon tiles, and with having those tiles in, what happened is they found out that the tritium actually was contained within the carbon tiles, and that meant your tritium retention was actually in your vessel. You couldn't get it back out again. So they really wanted to have it so they didn't have the retention of all your tritium in the machine, because they needed that to be able to put into the plasma. So they actually changed from the carbon tiles to these beryllium tiles, and there's tungsten down the bottom in the diverter because of the very high heat loads. We also have a tritium handling plant. I'll just show a picture of that later on. And we have up to, although we're just working on, we just close down shortly because we have the neutral beam system, I'll explain that shortly, that can give us somewhere, we routinely have 25 megawatts, but it's meant to be able to deliver at some point up to 35. Okay, starting with some of the systems, when I was doing this and bringing it together, there is so much work and so much engineering that all comes together to operate this one system. And the first one is we have our own 400 kV feed coming directly off the major grid. Now this is great. This can provide us with about 500 megawatts of power. Unfortunately for us, we need twice that. So what happens if we took that off the grid? I don't think Oxfordshire, or in fact many people would be very happy, and their lights are dimming every time we went up. So what we do have is we have 2 huge flywheel generators, each able to deliver about 400 megawatts each. So I'll turn these on there. So this is the power supply. As you can see just on here, this is our own 400 kV feed, and actually if you go to the electricity board, you can see jet with a little pylon on it, and we're dedicated. And we do have a red phone to say, Coronation Street is starting, please don't do any plasmas. Similarly to that, they do tell us we have what they call trial periods where we're not allowed to operate. You can see here some of the feeds, the 400 kV feeds, and then the 36 kV feeds that then go out to all the separate plants. So I've got some on the iron-cyclotron resin heating system, which is the RF plant, to feed my systems, and similarly for a lot of the other systems on jet. So, flywheel generators, these are impressive. I'm very impressed with this. The engineering that goes into this is fantastic. We've just had problems where they've had to level it and get they had some vibrations, and they couldn't have that, especially with the weight of them and the fact that they rotate 225 revs per minute for about 10 minutes before the pulse actually goes. So as you can see here, there's the pit before it goes in. There's the flywheel in there. And that's the 8 megapony motor sitting on top. It would fit in probably bigger than this room for the flywheel generator itself. And there's 2 of those. And pretty much, I'd have to think about where it goes, but if you turn it on its side, it can go about 30 miles. Just with the energy it actually gets in it when it's running. So that's the power supplies, but we've got other things to think about. I told you that we had a bootstrap current which gave us about a heating effect of 50 million degrees centigrade. So how can we then increase that to be 150 million plus? And the way we do is we've got 2 systems, or we actually got 4 systems, but the 2 systems I'm going to explain tonight is the neutral beam system, which is this one coming in on here. There's a lower hybrid system, and there's also the RF generation system, or the iron-cyclotron resonant heating system. The reason it's called iron-cyclotron is it's just the way it interacts with the ions in the plasma. So to start off with, for these heating effects, the first one is the neutral beams. Now, clearly, we've got a magnetic field around the outside, because I've told you that's what's contained in the plasma. So how are we going to get this energy in if you've got anything that's got any sort of charge on it? So what you have to do is you have to have a neutral source going in. And the way they do this is they start first of all, is to get some fast ions going. So they drive the fast ion beam into a colour emitter like that. But of course, that's got charged particles. If you threw that in at the moment, it just deflects straight in the wall, put a big hole somewhere. So they can't do that. So what they do is they introduce a neutralising gas. And they get this composite beam, which effectively takes off all the charges. But you will have some residual charges within that, which you can then deflect off by putting a bending magnet in. And then you have a cooled ion dump in the bottom, so you take all of that off, and you leave yourself with a neutral beam. Now, these are fast particles that we want, but there'll be some slow particles still in there. So you also need to have a good vacuum in there. So they've got cryogenics in there as well to try and make sure that any of the slow particles are taken away. So all you're left is with your fast energy beam going through to the plasma. And that's at the moment we've just had we've been trying to get up to 30 megawatts of power from this system, but we routinely operate about 20 to 25 megawatts into plasmas. As you can see, to give you an idea of the size of that, so the man standing there, you can see there's 8 iron. So these are the iron pinnies, as they call, negative ion sources. And as you can see, there's 8 on there, and then also there's 8 on the other side, and they provide all the megawatts of power. We also do some diagnostics that I haven't included in this talk. This is the iron-cyclotron resin heating system. This is a system, as I say, 23 to 57 megahertz. We have 16 generators, so technically if we run into a test load, which is a match load, we can get 32 megawatts of power. Unfortunately for us, the plasma doesn't give us a match load, certainly not a characteristic impedance. So what we have to do is we've got some, and this talk doesn't discuss this, but we have some matching principles so that we can actually match as best we can to the plasma to get as much power as we can. We used to have a different type of 2-strap antenna, which gave us 22 megawatts of coupled power and some plasma. And with this particular scenario, we've had 60 megawatts of power. And we've also now installed, which is this one, what is called the IET-like antenna, which has a matching system of capacitors actually just in the vacuum chamber itself. So we've got 5 antennas that are in there. We have 16 2 megawatts RF generators, frequency we've explained, and they've got the HVD supplies that you saw coming from the 400 kV feed, so we've got 37 kV feeds on there. We've got 4 4-strap antennas, as you just saw in the previous thing, with getter pumping, so they've got vacuum scenarios that we have to look after to make sure we keep the vacuum. But meter-like antenna. We have 84 metres of transmission line, and I'm not talking the outside or outer transmission line is 30 inches, the inner 9 inches of copper, and that has to be able to withstand 50 kilovolts on the line. But we routinely operate at about 35 kV. And we have 3 different matching systems, and if anybody's interested, I can sort of explain that. The 3dB system, an external conjugate T, and the capacitor matching in the ILA. And that helps us to try and heat the plasma. This does it through the ions, so it's a very different way of doing it. And if we've got to have current drive in our future devices, this is one of the ways it could be used. We then have, in here, there's a low hybrid system. This is a 3.7 gigahertz system. Now this is, the reason it's called a low hybrid is because the frequencies at the lower end, it can actually heat electrons as well as ions, and that's why it's a hybrid, but it's the lower end of the frequency range. The higher end would give you electron cyclotron resonant heating, which is, at the moment, they're looking about 170 gigahertz for the electron cyclotron resonant heating. And you can see there's the klystron that they use. It's with the collector, which is got the lead shielding on the top of it. We also have a gas, as I say, JET is the only place in the world at the moment that can handle tritium. And so we have a gas handling system, and we're authorised to have 90 grams of tritium. And the way we get our tritium at the moment is it comes from, for us, it comes from Canada. And we're looking in 2017, 2018, to run JET with a full tritium campaign, which will then finish JET just before ITER starts. At the moment, that's planned 2017, 2018. And to do that, what they're also looking at is to put a detritiation system in and commission it, so it's all ready for those particular experiments in the future. One of the really good systems on JET, and I remember I said about we changed carbon tiles to beryllium tiles. We don't really want to put people in the environment within the torus because you've got beryllium, and anybody who knows if you've got beryllium in there, it gives you thin fibres, similar to asbestos. You get the thin fibres embedded in your lungs, you'll get what they call berylliosis. So what they do is people, if we have a beryllium handling facility, we put those people into suits and make sure that treat them as if they're going to be allergic to that and keep them away from that. So it's a way to stop people going into the machines is to use this particular man-in-the-loop system with robotics. And the way that happens, as you can see on the bottom left-hand picture, there's a boom that comes in, and this boom can come in at octave 1, and there's a boom that can come in the opposite side of the torus on octave 5. And what they can do is they can put in different, either a manipulator arm or a carrier arm on one side, and they can have a system where they can have drawers and things where they can actually feed things in. And then that means they can take things in and out of the torus, likes of tiles, and then keep the people outside in an environment that's a lot better for them. They changed all the tiles in there, there were thousands of them. This has proved to be a very, very useful system, and something that is certainly proposing to put on ITER and future devices. And in fact, it will be essential for any future tokamak or device that they're going to be doing to have this sort of system working. So can we improve the tokamak? One of the things is about if you take JET, it's very large, round, so can we make it a smaller, spherical, and then more compact? And this is what we do with the spherical tokamak on there. I'm only doing a short bit about this to say that we are doing work on the MAST experiment. And it's very important because they're actually doing some futuristic work that might help us with solving some of the fusion problems. And that's on the diverter, which says is the exhaust system at the bottom. So it's confined in a tighter configuration. And this one, where instead of being a donut, which is probably like the torus, the Masters experiment is more like an apple cord. As you can see on there, it gives a tighter aspect, and it could be a future way of having fusion instead of the torus and the bigger devices that we have at the moment. But there's still a lot of work to go on in that progress. So as you can see, here's the devices. This is the mass machine in there, and this is what they're proposing, because we're doing a huge upgrade at the moment. So if you look on our website, you can see the upgrade we're doing. So we're going to increase the pulse length, so about 10 times more pulse length, provide more heating power, that's through neutral beams. We're going to, instead of having the diverter at the bottom as you saw on the jet machine, it's actually offset, and they're hoping that this would then reflect and get the particles out in a far more convenient way, but they're going to have to do that testing in the future. So that's just a very, very brief introduction to MAST, and as I say, they're working hard on that at the moment and getting it upgraded for next year. So really, one of the things, having just given a brief explanation of a few of the aspects of the engineering problems and things that we use at JET, one of the things that you have to, what are we doing, how are we progressing towards fusion? And everybody says, and I'm without saying, fusion's 30 years off, when are you going to get it done? It's always going to be 30 years. And I'm going to come in there. What I will say is you can see from here, you see from the accelerators there, you can see the Pentium 4 at the top there, that's the progress of computers. Now, I started off at Torness Power Station, and I used to go and work in computer rooms that were filled this full. And now you're all asked this evening to turn off your phones, which are in your pockets. So it gives you an idea, that's the progress that we've made with computers. And look at the progress we've made with fusion. It's huge. And it's actually huge with a very finite budget that we've had over the years. Oops. So, and here you can see some of the progress we've made. So we've got here Q equals 0.65, and this is a jet. This is a pulse machine. And the reason it's pulse is because the magnets in there are not superconducting magnets. They're not cooled, so you can only put so much flux through the central core, and therefore they will only heat up, and therefore you'll have to cool it. So we have about a minute. Is about the longest pulses we have, and then we usually have a 20-minute cool-down period. But in 1997, we put tritium in the machine, and you can see we've got Q equals 0.65, and then we're going to do these tritium experiments later this year, which hopefully will get towards Q equals 1, but we'll never get the confinement time because we're a pulse machine, so we're never going to get the 5 to 10 seconds. And that's proposed for the next machine, IET. Now, one of the things that JET doesn't have, in fact none of the machines have, is it's fine, we're doing fusion, this fusion's working, but how on earth are we going to get power from it? So you're going to create fusion, you're going to have it. So one of the things they're looking at, that has to be developed in the future, is a lithium blanket. So if you put lithium on the inside and you get 14 MeV neutrons hitting that, what you can get is you can get tritium, and you can also get heat off, and then you can use heat in a conventional way through your turbines and get your electricity. Now, all that work, all that engineering still has to be done. So we're looking at how that could be done. And what is, this is sort of the proposal of how this was done, the sort of deuterium fuel, the tritium, and the helium. And all of that work I've been to kit, and there's a lot of work being done on the first wall blanket wall. Now, the future is, as they say it's always 30 years off. Actually, they're standing by the word. What they're doing is they've come up with an EU fusion roadmap, and that's available. Anybody can go and see it. And if you take this through the roadmap, you'll see pretty much what they're hoping is by 2050 they'll have a demonstration reactor. This is where they can demonstrate that they can get power into the grid. I have to say this is the EU roadmap. I think China have a completely different roadmap, and they've got very much a more aggressive roadmap. We're doing it very step-by-step through IET. I think China are going to go for it and try and get a full working demo, probably about 2040, I think is what they're proposing. And they have East at the moment, I know they've got an aggressive program. So Europe is doing it very conventionally, and China are doing a very aggressive program. Having said that, we do work with the Chinese. So here's ITER, the International Thermonuclear Experimental Reactor. This is being built in the south of France, and I'm sure you've maybe read about it. It's twice the dimensions of JET, so it's about 10 times bigger. And this one has now got superconducting magnets. I've been on the site, and the size is just colossal. So I think demo is going to be quite a challenge, let alone what ITER is. It's designed to produce 410 megawatts of power, and they're trying to get a Q equal 10, so they're trying to get 10 times more power out than they're putting in. And pretty much we've got everybody represented on the ITER project. So there's Japan, Korea, there's Europe, India, and the USA, and so pretty much the world of Russia. We're all there. And all these people I get to work in. And if there's one thing about being united, it's united in fusion. I've also been across to Brazil, so I would actually say that Brazilians are also in this. So I don't think there's anybody in the world that's not interested in fusion. So ITER, construction costs are currently at about 14 billion, and everybody says, well, that's a huge amount. It's 23 billion spent on the Beijing Olympics. And we're trying to do something for the future, and yet for 2 weeks or 4 weeks, then for the Olympics, it gives you a real scale of what we're trying to do with a very, very small budget. This is being built in Culham, the south of France. Every time I go, it's absolutely freezing. And construction began in 2007, 2008. And we're hoping that they're going to operate probably in the early 2020s. There are some hiccups they're having at the moment, but we're hoping that will go. But to give you an idea, this is how it's been started. I was out there a while back. These are the older pictures. I haven't got the new ones I took. You can see how it's been built up. So there's the top map, there's the walls building up on there, and then you can see the base there. So there's a lot of progress. But what you can't see is how big that site is. If you look going backwards on there, you can see they put all the power supplies in for the 400 kV feeds, all that's in. And they've got a big, huge, massive building at the back, which they're using to build the coils. You can get an appreciation. So you can see on the end there, you can see where all the power supplies are coming in off the grid to feed all of this. And you can get an impression of the actual massive size of ITER. So I thought about the challenges of fusion, and I've got my own ideas, obviously. I thought, wait a minute, let's go to the roadmap and see what they think the challenges are going to be. So I've actually taken the missions out of the roadmap to demonstrate that. So mission 1, plasma regimes of operation. A lot of the tokamaks around the world are operating on this. Keep the plasma stable. We have instabilities on the edge with edge localized modes. If you have disruption, especially later on a machine such the size of ITER, it could be colossal. If you think that JET has moved 9 millimeters when it had its disruption. You need a heat exhaust system. One of the things I've said is you have the diverter down the bottom, and one of the problems is you've got all the heat loads that are going to be on there. So is that going to be sufficient? Because it's a cryogen system, so you capture molecules and then you want to release them, so you've got to heat it back up. That's going to put a time constraint on how often you can use the plasma, because you're going to have to stop and start. So, but you have to have it actually realistic to be able to generate power. One of the big things, certainly for engineering, certainly things that we're interested in, is neutron resistant materials. There's a huge question about what materials we could use. This is probably the biggest stumbling block that we have currently. And in fact, there's a facility that's meant to be built shortly, it's called IFMIF, where it's going to look at this, where you can bombard these materials with these high energy neutrons to be able to test them, to see whether they're going to be able to withstand the harsh environment. Certainly it's going to come up with a demonstration model like Denver. We have to have something we've not done yet. We're getting tritium from the power plants of the nuclear stations around the world. So at the moment we get it from Canada. But what the thing is, if you put lithium, you're going to get tritium out, so it's hitting as lithium, you're going to have to somehow have an engineered solution to get the tritium, and you're going to have to then get that out, reproduce it, get it back in. That's all new engineering that's never been done yet. So they're sort of things that you're going to have to think about. And then how's that going to be intrinsically safe? Tritium in itself has a half-life of 12.3 years, and it also, the way it's a beta emitter, so you have to make sure that you've got facilities around there to keep people safe and the machines safe. We need an integrated demo design and systems development. So we've got lots of diagnostics on JET. What we're going to have in the future, what diagnostics are needed across a demo thing. Do you need them all? What are the key principles you're going to need in a demonstration machine? One of the things, we're coming into a mature market, that makes it very much harder. Everybody says, well, we don't matter, we've got it now. So how are we going to get this so we can do it in the future? We need to have this competitive, and a lot of the industry at the moment says fusion's too expensive and we can't say it's going to be right. The other thing is stellarator. I don't know if anyone knows stellarator. I said we've got toroidal, colloidal, and then you need to drive current through it to get your magnetic fields and your helical field lines. What if you just make the machine helical, and therefore you don't need to drive current? And that's what effectively a stellarator does. So if you go to Germany, at the moment they're building that, and that should be operating or starting up shortly. So it's just slightly behind the maturity of JET and probably some of the other tokamaks, but you should not dismiss it. As I say, you shouldn't dismiss anything. It could be something in the future, you don't know now. So in summary, and thank you for all listening, I think personally we're making huge advances in fusion technology around the world. With all the people I work with, there's got new things happening. It's developing at a very, very fast pace, and there's a lot of people very, very interested in this as a possible potential way of providing our energy in the future. But developing the right materials is a real challenge. So all those engineers, if you've got any ideas of how you think you could develop these materials, I think would be very interested people, because I think there's an awful lot to be done there. The maintenance, one of the things I was considering, how do you maintain a fusion power station? You can't just go out and take something out and just replace it, or a wire breaks. You have to really, really think of how it's going to be maintained. And they've got very novel ways of effectively making modules that can be taken out and removed and things like that. Think of that engineering, it's huge, it's colossal, and engineers have to work towards this. The machine needs to operate for sustained long periods of time, so you can't just go on, off. You need to have it there. So how are you going to keep it sustained? How are you going to keep introducing the gas? All of those things all have to be solved. And the first wall components we haven't even started on really. I know there's kits working on them, there's a lot of places around the world that are doing that, but we've not fully tested them on how they're going to work. Especially when you've got the cooling system, how are you going to do that? And how are you going to extract the heat out of the system to be able to then get it into electricity? So all those first wall components. But having said that, and just as a thing, maybe one day we'll see this in real life. So thank you very much for your attention.